Hi everyone, welcome back. So today we're going to continue our lecture series on electromagnetism. Today would be lecture 20 and we will start discussing waveguides. So in the last lecture, we looked at plane wave reflection and transmission at an interface between two dielectrics. And at the end, we also looked at what is called the Fabry-Perot resonance, where you have two interfaces and three dielectrics. And you can have this kind of resonance phenomena, right? So we'll kind of build up from there and see how that can lead us into waveguides. Okay, so if I go back and draw that same Fabry-Perot picture, I have two interfaces. Let's say I have a dielectric medium here, epsilon 1. This is epsilon naught and epsilon naught. It can be anything, it doesn't matter. And we said that, okay, if I have a wave coming in here, then part of it goes in, comes out, and then there's reflection. And then there's reflection here, and so on. And at each reflection, there is some transmission as well. Right, but earlier we had also introduced this concept of total internal reflection, where essentially when I have total internal reflection, there is no transmission through this medium. Right? There's only reflected wave. So if I come in from here and I have total internal reflection, then what happens? At every intersection, at every interface where I have a reflection, I don't have any transmission, which means I only have a wave that's going to keep bouncing back and forth inside this. And it propagates essentially in that direction. And that's an example of a waveguide. So a waveguide is a structure that guides an electromagnetic wave. Okay, so which means that electromagnetic wave is somewhat confined inside this medium. Okay, by bouncing back and forth. So this is of course a slightly simplistic model, but even the simplistic model of ray tracing and looking at how these waves bounce back and forth is not inaccurate. Excuse me. It is still valid and it can actually give us quite a few insights. So let's take a look at those. So let's say I have a wave that came in and reflected off of this boundary. Maybe I should redraw it. Came in, reflected off of this interface. Something like that. And then went back up. And then so on, right? So I label some points. So we'll call this point A. So point A corresponds to where this touches this axis. Okay. Yeah. So this would be A. Let's call this B. And let's call this C. And I'll draw a perpendicular straight down from B. Right? And then I take an image of BC. So this is the image of BC. And I'll call this B prime C. Excuse me. B prime C. Okay. Now, if I look at this ray that was coming in like this has some wavefront associated with it, which is perpendicular to the ray. So these are, let's say, the maxima of that wavefront. So if I draw that wavefront at B, I'm just going to draw it like this. So it's supposed to be perpendicular, but I'll exaggerate it out a little bit. Maybe draw it like that. Okay. So this is not geometrically perpendicular, but if I drew it perpendicular to the way I had it here, then it would show up here somewhere. But in reality, okay, this is supposed to be very shallow, and it turns out like that, right? But you get the idea. Okay, so then this point BE is the wavefront of the ray AB. Right, so AB is a ray, BC, and we saw that each ray corresponds to essentially a plane wave, right? So we have one plane wave essentially going this way and another one going this way. And if you think about it, this plane wave and this plane wave are really the same plane wave because they're both associated with a wavefront that's like that, right? And then you have another plane wave like this, and that's another plane wave like that. So essentially these guys have a wavefront That's like that, right? So this kind of wave that's bouncing back and forth corresponds to two plane waves, one in that direction, one in this direction. Once you kind of understand that, then the rest of it is kind of a little bit easier. So let's say I'm coming into an angle theta I, then of course this angle is also theta I. Okay? And I'll draw another wavefront, which is the wavefront at the point C. So this is my wavefront at point C. Call this D. So this is also perpendicular. Now, keep in mind that the wavefront at point B, which is corresponding to this one, and the wavefront at point C belong to the same plane wave, right, which corresponds to this one. So essentially, if I draw it all out, right, this is a plane wave, and that plane wave kind of continues and becomes the wavefront for this ray as well, these two rays, which means BE and DC correspond to wavefronts that are both for the same plane wave. Okay? Okay, so if they correspond to the same plane wave, and I've drawn them as wavefronts, then the phase difference between them, or they need to have essentially some phase relationship, right? Because they correspond to the same phase front, this one and this one. Okay, so what does that mean? That means that when this wavefront went from this location to this location, it picked up some phase in that direction, right? So if I start from this point and I go to this point, this phase over this region, so basically this phase must be the same phase in the ray picture that I got from this point to this point. Right, so the phase propagation along this direction or phase accumulation along this direction and the phase accumulation of this wavefront have to be the same in order for them to be the same wavefront or belong to the same wavefront, right? So either you take the ray picture or you take the wavefront picture, you should get the same phase accumulation. Okay, which means what? Which means that BC must be equal to EC, right? This length must be equal to this length. Because the way I've drawn it is not the case, as I said before, but hopefully you can kind of see that that's the case. Now, strictly speaking, this is not true. It doesn't have to be equal to EC. They just have to have a phase relationship. Since this point, whether you reach this point as a wavefront advance from this location or whether you reach this point from this to here, they both have to have the same phase. For them to have the same phase, you don't need these to be equal. What you need is for BC minus EC times K, which is the total phase advance, to be equal to 2m pi. So if you kind of understand that, then it makes sense why you have specific. We will see that if you understand this part, it will give you quite a bit of insight into waveguides. Okay. So of course, BC minus EC is B prime E, implies that B prime E times K must be 2m pi. Right? And what is B prime E? It's this length. And that length is nothing but this total length times cosine theta I. And this total length is two times the thickness of this. So if I label the thickness of this guy as T, then implies that 2A or 2T, I should say, 2T times K cosine theta I is equal to 2m pi, which implies that theta I is equal to cosine inverse of m pi over AK or TK, not AK. And this is an important relationship. So what is this saying? This is saying that the incidence angles at which I can satisfy that phase relationship, where this point is a phase advance from here or a ray advance from here, only happens at certain angles. So only these angles can support a plane wave propagation or a wave propagation in this waveguide. Okay, so if I come in at this angle, then it satisfies this phase relationship and that propagates. Come in at another angle which corresponds to m equal to 1, it works. Now, if I come in at an angle that doesn't satisfy this relationship, then this wave actually cannot propagate. And what happens is that it gets reflected back. Okay, or it evanescently decays inside, which we'll see later, but that's intuitively this is what's going on. Okay, so essentially, the waves that can propagate have certain specific angles. Okay, so m equal to 1 is basically when theta I equal to 0. You have wave propagation in this direction. So this is 0, 1, 2, minus 1, minus 2, and so on. Okay, and this is actually nothing but the angular spectrum, because this is describing all the plane waves that make up the mode or the wave, the final wave that propagates inside your medium. So if you go back to the simplistic case here, we have that maybe this is m equal to 1 and this is m equal to minus 1. So these two plane waves, which are all the same, and these guys are all the same, all of them correspond to one k vector. This corresponds to the negative of that k vector. Now, of course, you could have something maybe like that, maybe like that. Now, why can't you have very large m? Because beyond a point, you don't have total internal reflection, right? So you can't have maybe m greater than 3 or 4. Depends on the waveguide and depends on these values, and depends on the material. But essentially, your m can only be discrete values, or your theta I, your k space, or your angular spectrum is discrete. Now, this is very different than in free space or in a homogeneous medium where we saw that you can have plane wave propagation in any direction. It is not confined to a discrete set of modes or a discrete set of vectors. You can have a continuous spectrum. So essentially in a homogeneous medium, plane waves can propagate in a continuous spectrum, whereas in a waveguide, typically in a waveguide, that is not the case. Right? You have a discrete spectrum. And we were able to arrive at that without any kind of equations, just from this intuitive picture. Okay, so now that we kind of developed this intuition, now we can formally introduce waveguides and study how they propagate and what kind of modes they can support. That's what we'll do next. Now we saw that, okay, you can have a discrete spectrum, but it may not be always convenient to represent the waves that are propagating inside a waveguide as a combination of these plane waves or in terms of the angular spectrum. Instead, what we would like to see is what are the solutions that we can directly get for these kind of waveguide problems. Okay, in order to do that, we need to introduce a new set of solutions called the TE and TM modes. So let's do that next. So we have they're called transverse electric and transverse magnetic field solutions. So another way to say that is that we have wave equation, we saw it can be solved for TEM mode or plane waves and plane waves on a basis. The TE and TM field solutions give you a different basis than the plane waves. And this is a more convenient basis when we want to discuss waveguide problems. Okay, so rather than having to look at superpositions of different solutions as a solution to your wave equation in a waveguide, the TE and TM solutions would directly give you the right basis. So you don't have to deal with superpositions. Okay, so essentially these TE TM modes will directly satisfy your waveguide boundary conditions and give you a complete basis similar to how plane waves gave you a basis in free space. Okay, so let's arrive at this TE TM solution. If you recall, we had the Hertz vector potential, which satisfied the vector wave equation in a source-free region. And we had the Hertz magnetic vector potential, which also satisfied vector wave equation in source-free region. And so we'll use this Hertz vector potential to develop TETM solutions. And if you recall, the electric field in terms of the Hertz vector potential is gradient of divergence of pi plus k square pi plus I omega mu curl of pi m, and h equal to minus I omega epsilon curl of pi plus gradient of divergence of pi m plus k square pi m, right? Okay, so TE, what does TE mean? TE stands for transverse electric, and it just means that the electric field is perpendicular to k hat. Okay, so if I have k propagating in some direction, then it is perpendicular to the electric field. And k hat is not perpendicular to the magnetic field. So magnetic field has some component along k hat. And that's what transverse electric means. And transverse magnetic is the other case, where the electric field has a component along k hat and the magnetic field is transverse or perpendicular to k hat. So we'll start with the TE solution, the transverse electric solution, and see how we get there. Okay, so we see that, or I should say it is known that if I set pi equal to pi z, z hat, this gives me the TE solution. And if I set pi m equal to pi mz, z hat, this gives me the TM solution. So this is sort of a known fact. We'll assume we know that, and we'll show that, okay, if I take pi to be this form, I get this TE and TM solution. Of course, you can also try other kinds of pi. You don't have to rely on just these, but we'll see that, setting pi to be pi z along z hat or pi m to be pi mz along z hat will essentially give us what we want. Okay, so that's kind of a known thing. We haven't really proven it, but we'll see that that is indeed the case. Okay. This is the other way around. So this gives me Tm and this gives me T. Okay. All right, so the one way to kind of quickly see this is to show that pi m must be equal to 0 for the Tm solution. And similarly, pi must be equal to 0 for Te. Why is that? If I want Te, that means my electric field has to be tangential to K, right? Okay, now if I go back here and I said that, okay, if let's say K is along Z hat, okay? So say my K vector, say K hat is Z hat. So under this condition, I should say that when K hat is Z hat, when K hat is Z hat, then pi equal to pi z z hat and pi m equal to pi m z z hat gives me the Tm and Ta solution. Okay? So this is essentially Tm to z and Te to z when K is along z. Okay, so having said that, now if K hat is along z hat, then if I want to get the Te solution, then E cannot have any component along z hat, right? And for E not to have a component along z hat, this must be equal to 0 because pi has a component along z hat, right? So we need to set this to 0, and to set that to 0, pi must be 0. And similarly for the Tm solution, we know that Im has to be 0, otherwise H would have a component along z hat, right? And that's the reason that pi m must be 0 for Te and pi equal to 0 for, pi m must be 0 for Tm and pi must be 0 for Te. Okay, hopefully that makes sense. So given that we know that, then essentially, let's say we are going after the Tm solution. So for the TM solution, since pi m is 0, E is nothing but gradient of d pi z over dz plus k square pi z, z hat. And that is directly from this equation. Divergence of pi is around just z hat is dz over d over dz times pi z, gradient of that, plus k square pi z. Okay, that's what I've written down here. Okay, so now we want to do is we want to split this delta, is the Laplace operator, into a transverse part and a z component. Okay, where this is nothing but d over dx x hat plus d over dy y hat. That's the transverse part, subscript t. And doing this, we can write E as d over dz transverse gradient of pi z plus d square pi z over dz square plus k square pi z. And this whole thing is under z hat. So all I've done here is that I separated this into these two components. Now this component, when it applies on this, you get this part. And then you're left with just this and this. And then I pulled the d over dz out and I took this term inside. That gave me this term. And of course, this term is the same as this. Okay, so nothing special, just some manipulation. You can also write h as minus I omega epsilon delta t I z cross z hat. Okay. And this also comes directly from h, from the equation for h out here. Okay, so you can separate this into pi t or delta t and d over dz. And this only has a z hat component, so cross with d over dz, z hat goes to 0. You're left with just this cross with the delta t cross with this, and that's what this is. Okay, with one vector identity involved. Okay, so if I go back to the wave equation, what does that look like? That's pretty simple. Pi z d square over dz square pi z plus k square pi z equal to 0. Okay, so we said that we are kind of interested in direction of propagation k to be along z hat, and that's the kind of solution we're looking for. So we're looking for solutions of this kind. Pi z equal to psi of x comma y e to the plus or minus I beta z. Okay, so this is some waveguide, some modal distribution in x and y. So this is some scalar function in x and y. It can be something random in some x and y. And all of that is propagating along z. So that's what this is saying. So I have some field distribution in x and y, or some mode distribution in x and y, and that propagates along z. Yeah, that's what this is saying. So there is no variation with respect to z except for just this part. This is the kind of solution we are looking for. Okay, so if I do this, then now I substitute this into the wave equation, and that gives me a scalar wave equation with respect to psi plus kc square psi equal to 0. Okay, so this is a 2D wave equation. Right, so essentially we went from the vector wave equation to a 3-dimensional scalar wave equation, and from that into a 2-dimensional scalar wave equation. And that's nice, right? So how did that happen? I mean, when you substitute this in here, this component doesn't act on this. So you're only left with this part. And then this component acts on this and brings down a beta square, a minus beta square. And then you have a k square out there. So essentially you're just left with, what is this? This is nothing but, write it in. So kc square is k square minus beta square. So it's good to interpret these terms. So k square is the wave number of any wave that's propagating in this given medium, right? This is the wave number for a wave propagating in this medium, assuming it's homogeneous. Okay. This is the wave number along Z. Okay, and this is the transverse wave number. Because it satisfies the transverse wave equation, right? So essentially kc square plus beta square equal to k square is very similar to kx square plus ky square plus kz square. Right? This is also a dispersion relation. I have a transverse part, I have a z component, and I have a k square. Okay? All right, so given psi, once we solve this wave equation for certain levels, so certain boundary conditions, which we'll see based on different waveguides, then we can get E and H directly from it, which are given by E equal to plus or minus I beta gradient of psi plus kc square psi z hat multiplied by e to the plus or minus I beta z. And the plus or minus correspond to forward or backward propagation. H is minus I omega epsilon gradient of psi cross z hat e to the plus or minus I beta z. Okay, so this is for Tm. This is the Tm solution. You can kind of see that it is indeed Tm because you have some component along Z for the E field, but for the H field, there is no component along Z because it's crossed with Z, right? Okay, and you can do the same thing for TE. Or before we do that, we should also specify that ZTM is a constant, which is defined as Z hat cross E divided by H transpose or HT. It doesn't have to be T, it can just be H. So H is already transverse. And so that's nothing but this term divided by this term. Okay. And that is nothing but beta over omega epsilon. And this is called the Tm wave impedance. Okay. Now, similarly, you can do the same kind of development for TE, which I'm going to skip the details. Right? It's obtained from pi m equal to pi mz z hat. And you can derive all the fields and you'll get H equal to I beta del T psi m plus kc square psi m z hat all multiplied by e to the plus or minus I beta z. And E would be I omega mu del T psi m cross z hat times e to the plus or minus I beta z. Okay. Similarly, ZTE, or I should say actually YTE, which is the admittance of the TE mode, is defined as minus z hat cross H transverse or H, because anyway the transverse gets removed when you, or the part along z hat gets removed by the cross product, divided by E equal to beta over omega mu. So this is the TE admittance. Okay, and if you actually look at the fields, they're nothing but duals of the TM modes. Right? So you don't have to solve it from scratch. You can just apply duality to the E and H fields, and that will give you the H and E fields for the TE case. Okay, so this is essentially the framework under which we can extract the TE and TM modes for a given wave equation. So in order to actually find what the modes are, we need to solve for a few things. We need to first solve for, we need to solve this wave equation given certain boundary conditions based on what kind of waveguide you're working with. And we also need to find a dispersion relation, right? What is beta for a given medium? Right? Either once we know beta, we can find Kc, or you find Kc and that gives you beta. Right? So these are really the unknowns, this one and this one. And different waveguide problems will give you essentially different solutions for this and this. And that's what we'll take a look at next. We'll do this on a new page. So the first waveguide we're going to look at is essentially what we discussed at the beginning of today's lecture, which formally is called dielectric plate or dielectric slab waveguide. Okay, so the geometry looks very similar to what we did earlier. You have a slab of some medium, let's say mu2 epsilon 2. Up here you have mu1 epsilon 1, mu1 epsilon 1. And this is, of course, some medium. And I'll draw my coordinate system as well. This is x, and this is z. Okay, and we assume this has a thickness of t. And we want to see what kind of TETM mode solutions you get inside this that propagate along this direction. Similar to what we did earlier with the ray model. Okay, so in this problem, there is no variation along z and also no variation along y, because we assume this slab is infinitely large in y. Okay, so because of that, maybe we start with considering the TM case. The ILZ, which is a function of only x comma z, it's not a function of y because there's no variation in y, is psi Lx e to the I beta z. Right, so psi is not a function of y because there is no variation in y, and this L corresponds to the subscript for medium 1, 2, or 3. So I should write that down. This is medium 1, this is medium 2, this is medium 3. Okay, so L equal to 1, comma 2, comma 3. Okay, and psi L satisfies the two-dimensional wave equation, which now becomes one-dimensional because you don't have variation in it in y. Plus KLC square psi L equal to 0. And I'll call this equation star. Okay, L is the medium subscript, and KLC square is nothing but K square or KL square, because it's a different medium, minus beta square. Okay, so now you may say, okay, why did I write beta square and not beta L square? We don't need the subscript L because beta is the wave or the phase propagation along the z direction. And if you recall earlier, we said that when I have a medium, there is this phase matching condition, which ensures that the phase propagation along the boundary must be the same in both regions, on both sides of the boundary. Right? That's what we saw was the phase matching condition. So essentially, beta has to be the same in all three media in order for us to have phase continuity at the boundaries, and that's the phase matching condition. So if I put beta L, and I should say beta L is equal to beta for all L equal to 1, 2, 3. So another way to say that is just remove this part, right? Okay, and we're also looking for solutions where the mode is confined inside this region and it's not propagating in this region and this region. To prevent propagation in that region and that region, 1 and 3, we need to ensure that the wave is evanescent in 1 and 3. And we already saw that, right? In case of total internal reflection with the ray model, the wave is indeed evanescent in this medium and this medium. And that's what we're looking for. We're looking for solutions that don't propagate away in these regions and only propagates in this region. So one way to enforce that is to look for solutions such that K1C and K3C, right, which is the wave vector, transverse wave vectors, are imaginary in 1 and 3. So we'll call that some I nu. Okay, since we don't want propagation. So this gives a confined mode. So we're looking for this kind of a solution. Okay. So we can divide the solution space into two cases within TM. One is TM odd mode, and the other is TM even modes. Okay. So if I go back to this wave equation, which is just a one-dimensional equation, it's pretty simple. Solutions to this can be of the form sine or cosine. Like when I take second derivative of sine of psi, I get minus sine of something times KLC square, right? And that minus and this get cancelled, and I get z. So basically, psi L should be equal to sine KLC x, right? Then if I take second derivative, it cancels with this term. Cosine also does the same thing. So we'll treat the sine case as the odd modes and the cosine case as the even modes. Okay, so essentially, if I rewrite that, the solution for the odd case in region 2, x comma z, is a sine a2cx e to the I beta z. I1z, we want this to be a decaying exponential, which is b e to the minus nu x e to the I beta z. And in region 3, sigma z, this is minus b e to the nu x e to the plus I beta z. Right, so why do we need that minus sign? So what does this mode actually look like? So if this is my medium, then this mode looks something like this. It's sinusoidal in region 1, and then exponentially decaying in sinusoidal in region 2, exponentially decaying in region 1, and similarly sinusoidal in region 2, and then exponentially decaying in region 3. Because it's odd, it's an odd function. In this part it's plus, in this part it's minus, and that's why we need the minus sign here, right? Because this is negative and this is positive. Maybe the way I drew it, it doesn't look like it, but let me maybe redraw that. So, line like that. Something like this. Yeah, and this thing propagates in this direction or in this direction, doesn't matter. Here we're looking at forward propagation because this is positive. Okay. Okay. We also have the dispersion relations, which are K2C square equal to K square minus beta square, which is of course omega square mu epsilon mu 2 epsilon 2 minus beta square. And the other one was nu square because K1C and K3C are I nu equal to beta square minus K square which is beta squared minus omega squared mu1 epsilon 1 or mu3 epsilon 3, doesn't matter, right? So given that I know what pi is, now I can find the electric and magnetic fields. So I'll write them down. So we'll write them component wise, e to z, and I'll only write the z component, which we'll see in a second, y, k to c squared sine k to c x e to the I beta z. E1z is minus b nu square e to the minus nu z e to the I beta z. E3z is equal to beta nu square e to the nu x e to the I beta z. H2y is equal to IA omega epsilon 2 a to c cosine a to cx e to the I beta z. H1y is minus IB omega epsilon 1 mu e to the minus nu x e to the I beta z. H3y is equal to IB omega epsilon 1 mu e to the nu x e to the I beta z. Okay, and of course, E also has an x component, which I haven't written down. The reason I haven't written down is that once we know these values, or once we have these equations, now we can apply boundary conditions to find K and A. We don't know what A, B, K, 2C, and nu are. So in order to solve for those, we have to apply boundary conditions. And boundary conditions don't really apply to Ex, right? It only applies to the tangential part. So this is the tangential E, this is the tangential H. That's why I've only written these out. Okay, so apply boundary conditions on E and H at x equal to plus or minus t over 2. So what does that give us? That gives us a k to c square sine k to c t over 2 is equal to minus b nu square e to the minus nu t over 2. Okay, so I've just equated these two. Of course, you can also equate these two and it would give you the same thing once you substitute z equal to minus t over 2. Okay. And the magnetic field gives me IA omega epsilon 2 a to c cosine a to ct over 2 is equal to minus IB omega epsilon 1 nu e to the minus nu t over 2. Okay, so I need to solve these two equations for A and B and for K to C and nu. So of course looks like I have 4 unknowns and 2 equations, but that's not true because we already have relationship between K to C, nu and beta, right? Which comes from these guys. Okay, so we have 2 equations here. And then we have 2 more equations here. And we need to solve for A, B, nu, K to C, and beta. Okay, so we have 5 unknowns essentially, and 4 equations, which makes sense because you can't solve for A and B independently. You can only solve for their ratio, right? Because A and B are essentially the magnitude of these fields, and that depends on the excitation and how much power the mode is carrying. Right? But the ratio A to B is fixed. And the absolute values are not, but the ratio is fixed. And that's what we care about. So you really have the ratio of A to B. You have K to C, nu, and beta, and 4 equations. So now we can solve for them. Okay, let's do that. So if I take the ratio of these 2 equations, that gives me K to C over epsilon 2 and K to C t over 2. equal to nu over epsilon 1. And from the dispersion relations, if I add these two, so if I add these two equations, then minus beta square and plus beta square cancel, right? And that gives me another relationship between K to C and nu, which is, so I'll say sum of dispersion relations gives me K to C square plus nu square equal to omega square mu2 epsilon 2 minus mu1 epsilon 1. Okay, so that this is just two equations and two unknowns. These are my unknowns. Right? Of course, this is all known. This is all known. Of course, okay, this is also an unknown. So I can solve these two. Okay. Okay, how do you actually solve them? That's not so easy. But luckily, we can do it numerically. But even before we do it numerically, we can get quite a bit of intuitive insight from graphing it. Okay. So in order to graph it, I'll define x as K2C2, K2CT over 2, and y as nu t over 2. Then those two equations become epsilon 1 over epsilon 2, x tan x equal to y, and x squared plus y squared equal to omega t over 2, square root of mu2 epsilon 2 minus mu1 epsilon 1 whole square. I wrote it like that because this is the equation for a circle, right? And this is the equation for a line that looks like a tangent. Okay, so now we can actually draw this. So I'll only draw it in the positive quadrant because x and y have to be positive based on these definitions, right? So I have a circle something like that. And this circle corresponds to my x square plus y square equal to omega t over 2 square root of mu2 epsilon 2 minus mu1 epsilon 1 equation. And then I also have, let's say this is pi over 2, pi, 3 pi over 2, 2 pi, and 5 pi over 2. Then if I plot the tan function, this function, it looks kind of like a tangent, y equal to tan x with kind of a scaling factor x, which is like a skewed tangent. So roughly, what does it look like? So if I draw lines from all of these points, tangent function looks something like this. It goes asymptotically to infinity there. And then down here, it's kind of in the negative region, so you don't have anything there. And you have another asymptotic here, another asymptotic there, and so on, right? So the solution to this graphically happens when these two curves intersect. So these are your solutions. So you have one solution here, one solution here, and one solution here. Okay, so this is considered to be different modes. So this is mode 1, or I'll call this mode 0 maybe. This is mode 1, and this is mode 2. Okay, so these are all the different modes. So if you actually plot these modes, what do they look like? So mode 1 is the mode that looks like this. Mode 2 looks something like that. Mode 3 is that one, and so on. Right, so this is mode 0, mode 1, mode 2, and so on. Okay, so now when omega becomes smaller and smaller at lower and lower frequency, this circle comes in, right? Because omega decreasing, means this circle is becoming smaller and smaller, which means at lower and lower frequencies, you have fewer number of modes, right? When the circle is like this, you don't have a solution for this one. You only have two modes. Then when it becomes like this, you only have one mode that can propagate. So this is again for the propagating case because we've assumed that k and nu are all real numbers, or x and y are real numbers, right? So these are all the modes that can propagate inside this medium or inside this waveguide. And interestingly, for the TM odd modes, there is no lower frequency cutoff, which means when omega goes to 0, you always have a solution, right, in this direction, which is this mode. Okay, and that going back to where we started from, we saw that even at 0 angle, there is a mode, right, and that corresponds to this one. Okay, maybe that's not obvious to see, but that's the case. Again, it also shows us that you have a discrete set of modes, a discrete set of solutions, right? And this is your discrete space, solution space. And we also saw that in the beginning, you have a kind of a discrete angular spectrum, right? So some combination of those discrete angular spectrums will give you these different modes. That was the plane wave basis, and this is the TETM basis. Okay. Okay, so you can find a cutoff frequency. Cutoff frequency occurs when this circle intersects these points. So this is the cutoff frequency for this mode. This would be the cutoff frequency for this mode, and so on. Which means that when k to ct over 2 is equal to n pi, right? This is k to ct over 2. So when x is equal to n pi, pi equal to 0, this point or this point, for x of these values, you have cutoff frequency. And that is the same thing as omega t over 2 square root of mu2 epsilon 2 minus mu1 epsilon 1, because that's when the circle kind of intersects that. That's the radius of the circle. Right? So that gives you a value of omega, which gives you the cutoff frequency. This is for TM in 0 modes or in odd modes. And that's n over t times square root of mu2 epsilon 2 minus mu1 epsilon 1. Okay. N equal to 0 has no cutoff. So I should say n belongs to integers. Not integers, positive real numbers. Okay. All right, so that's for the TM odd modes. Now the TM even modes look very similar, which we'll quickly go through. So pi to z even x comma z is a cosine a to cx e to the I beta z. And then pi 1z, pi 3z look the same. So you apply boundary conditions and you get a dispersion relation that is cotangent instead of tangent. Epsilon 2 over epsilon 1 mu t over 2, right? And based on this, if you draw again the same dispersion relation plot with x and y, then that gives you cotangent, which actually does not have a solution that goes all the way down to 0, right? Because cotangent starts from pi over 2. It looks something like that. Then you have another solution here, which corresponds to 3 pi over 2. So which means that you have a lower cutoff, right? And you can show that the cutoff for the even mode is 2n plus 1 over 2t square root of mu2 epsilon 2 minus mu1 epsilon 1. Okay. All right. What do the modes look like? So the mode looks like cosine functions. Like that, that, like that. So that's n equal to 0, n equal to 1, n equal to 2, and so on. Okay, so the lowest cutoff frequency corresponds to Tm odd modes, Tm0 odd, and that's the fundamental mode, okay? Because that's the first mode that starts propagating. Of course, you can arrive at the TE solution by simply taking duality. And then again, there you'll have even and odd modes, and that completes all the different solutions for this problem. So this is an interesting or important problem because heterojunctions in semiconductor optics use these kind of slab waveguides. So solving for what kind of modes can propagate in them is very valid. Another important case is, which we'll look at next time, is if I set the lower medium to be PEC, then this just looks like a dielectric coating on top of a PEC, which is very, very broadly used. Right? In silicon chips, the silicon substrate is usually laid on top of some kind of dielectric, or even if it's in air, then you can have substrate modes that propagate in that silicon chip or in that substrate, and those are called substrate modes. Similarly, for a PCB, you have a dielectric on top and then air, and they can have substrate modes. And we saw that essentially substrate modes are nothing but this TMTE case. And interestingly, they can propagate even down to very low frequencies or 0, down to DC. And so this is a consequence is that the consequence of that is that substrate modes in a PCB can exist even down to DC. And that's why it's important to kind of understand how they get excited and how they propagate. And this is kind of the theory behind that. Okay, so hopefully that was interesting. In the next lecture, we'll move on to rectangular waveguides, which is essentially metal boundary condition, PEC boundary condition, and see what kind of modal solutions exist there. Then we'll introduce this concept of phase velocity and group velocity, and then look at modes that propagate inside a waveguide, what kind of phase and group velocities they have. And we still have to establish the fact that these modes indeed form an orthogonal and complete basis for any solution, and which is also something that we'll do in the next lecture. Okay, hopefully you're excited about that. If you have any questions, you can leave them in the comments. If not, I'll see you in the next one. Thank you.